4.3 part 3 deals with this concept of concavity. And concavity, broken down to its simplest terms, just tells us the direction that a function opens. So if we say a function is concave up, function is going to concave up. It opens up in this case. So that could be for all real numbers. So this one on the left, we have the domain all real numbers. Or it could be for a set domain, so over a closed interval. So this one we'd say from A to B. But the key is that the function opens up. You could also have a concave down function where the function opens down. So again, on the left is for the domain all real numbers. On the left, we got domain from A to B, so over the closed interval. So it could happen either way. And then you're also going to have functions today that do both. They open both up and down throughout an interval. So we're going to have a couple different tests to determine when they're opening up and when they're opening down. So the first one we're going to look at is the first derivative test for concavity. So for this, you must be given the first derivative graph in order to use this test. If you're not given the graph, then we're kind of out of luck on this. But when you're given f prime, what we're looking at is the slope. Okay, so we're looking at the slope of the first derivative graph to give us whether the function is concave up or down. So this first one, they say, if f prime is increasing, so you have a positive slope, then the original function is concave up. So here we go, we got the derivative on the left. You look at it, we have a positive slope for that function. Okay, so all the way throughout, we have a positive slope going on. It's linear, it's going up, positive slope. It tells me my original function is opening up for all real numbers. So positive slope, concave up. On the other hand, if the first derivative graph is decreasing, so we have a negative slope, the original function is going to be concave down. So looking at this, you have a negative slope going on, linear, it's going down for forever. It tells me that my original function is concave down for the whole domain. So using that information that we're just given, we want to figure out, okay, is the original function for these concave up, down, for what intervals is it happening? So for A, you look at it, f prime, okay, so we're thinking slope, f prime has a negative slope from negative infinity all the way till next value of 2. So that tells me that the function is concave down for that interval. So we're going to say from negative infinity to 2, because the first derivative, and we're going to get official here instead of talking about slope, we're going to say is decreasing. Okay, so that takes care of the concave down. As soon as I get to 2 and I'm going to infinity, we change around and we are now increasing. We now would have a positive slope. We're going uphill. So f is concave up for 2 to infinity because the derivative is increasing. There we go. Okay, so for part B, this talks about, or this gives us a little different function where we're going to have multiple intervals going on. So concave up, I want to know when is it increasing? It's from negative infinity to negative 2. And over here, so from 4 to infinity, because f is increasing, f prime is increasing. And then we're going to have a concave down when the first derivative is decreasing. So from negative 2 to 4. So from negative 2 to 4 because first derivative is decreasing. So that's when we would have a concave down for that function. All right, so that takes care of the first derivative test. And typically, like I said, you'll be given the graph on that, and you're just looking, when is it increasing, when is it decreasing? First derivative is going to equal concavity of the original function. Second derivative test. So you're going to take the second derivative, and we're going to go back to a sign chart or a graph. More times than not, it's going to be a sign chart that we're looking at. Okay. For this, the second derivative, we're not looking at increase, decrease. We're looking at whether the function's positive, negative. Okay. So what I mean by that, you look at this first one. F is concave up if the second derivative is positive. So this is where we're looking at our outputs. You have positives are above the x-axis, 0 on it, negative down below. So looking at this one, my whole function is positive for the interval a to b. And honestly, to match up with this graph, it should have arrows on the end of it. But we are positive, so we're up above. That tells me that, hey, my original function is concave up. If the second derivative is negative, so if my outputs are down below the x-axis, so in this case, negative down below, tells me it's concave down, it's opening down. So that's your second derivative. Or sorry, I was off the screen. When we're negative down below, okay, it tells us F is concave down, it's opening down. So that is your second derivative test. Okay, so we're going to use that information to answer whether the function is concave up or down. So here they give me a second derivative graph. We want to determine concave up or down for the original function f. This is where we go positives are up top, 0 on the x, negative down below. So we're going to be concave up. Here's my key point right here, 2 for 2 to infinity. Our justification, second derivative is positive. We're going to be concave down from negative infinity to 2. And our justification for that is the second derivative is negative. Okay, and now we're going to put it all together. So we want to first off sketch a graph of f of x equals x cubed. Okay, so f of x equals x cubed. It's going to be we have a point at 0, 0, 1, 1, and then we're going to go to 2, 8, negative 1, negative 1, negative 2, 8. Just going to have a function that looks like that. Okay, so I sketched the graph. I want to use the graph to tell where f is concave up, concave down. So A, when are we opening up? And this one you can tell kind of. The key point, the inflection point, which we're going to get to in a second, is at 0. So we're concave up from 0 to infinity. We're concave down from negative infinity to 0. All right. Honestly, it's going to get to the point where we're not going to be able to tell from the original graph where our key points are, our inflection points, where it changes. So that's where we're going to look at our first and second derivatives, really. First derivative is going to give me 3x squared. Go ahead and graph that. You got a point at 0, 0. Then we're going to have a point at 1, 3, negative 1, 3. So it's a real steep parabola. Again, we look at this when is, so when they give you the first derivative, we're looking for when is the derivative increasing. We are increasing from 0 to infinity. So I'm going to go ahead and put 0 to infinity. And then we're going to say f prime is increasing. Concave down is going to be when it's decreasing, so that's from negative infinity to 0. And then we're going to say that's because f prime is decreasing. Okay, last one we're going to look at is going to be the second derivative. So you got f double prime equals 6x. So that's just linear through the origin. And we're going up 1, 2, 3, 4, 5, 6. And then we're going down 1, 2, 3, 4, 5, 6. There we go. Okay, so remember for the second derivative, that's where we're looking positive, 0, negative. So it is concave up from 0 to infinity because our second derivative is positive. It's concave down from negative infinity to 0 because our second derivative is negative. All right, so I kind of thrown out this little keyword here a couple times, and it's called a point of inflection. And I had also mentioned that it's going to be difficult to see where it changes from concave up to concave down for a couple functions. So here's just a random function I've drawn here. And the points of inflection are roughly drawn in as these points, these dots. And a point of inflection is where it's going to change. The concavity of a function changes from up to down, down to up, vice versa, all the way through. Looking at this one, you can tell that it's very difficult to see where the function changes from concave up to concave down. In fact, you really can't tell from the graph. So this is where we're going to use a test to figure out, okay, where are these actual points? The test we're going to use is the first derivative test for inflection points. So you must be given f prime graph to use. Okay, so we need that. Inflection points occur at the x values where the derivative changes from increasing to decreasing or from decreasing to increasing. There's this mention of max mins. That's how you're going to think of it, but you can't justify that way. Okay, so we're looking at the first derivative graph, and I want to know, okay, when is it changing direction? So you are thinking max min, but you can't justify it that way because since we're looking at the first derivative graph, it's actually not the maxes or mins for the original function. When using the first derivative to justify, you must refer to the change from increasing to decreasing or decreasing to increasing, not as a max or min. Okay, so we're focused on increase, decrease for the first derivative. So we want to use following first derivative graph to determine where the original function f has inflection points. So we're looking increase, decrease. So where does it change? It changes here, changes here. Okay, so I'm going from increase to decrease, decrease to increase. So we want to know the points of inflections. And we're going to say f has points of inflection at x equals -1, x equals 2, because f prime changes from increasing to decreasing back to increasing. This probably isn't like the best wording for it, but you kind of get the point, okay? I say -1 and 2, and the reason being we're changing from an increase to decrease. So I go increase to decrease at -1, and that's a decrease to increase at x equals 2. So for B, I want to determine where will it be concave up, concave down. F is concave up -infinity to -1 and 2 to infinity because f prime is increasing off the screen, and then f is concave down on -1 to 2 because f prime is decreasing. Okay, so that's still kind of the easy one. You just got to remember that the first derivative, when it's increasing, we're concave up, decreasing, concave down. And then the last test we're going to look at today is the second derivative test for inflection points, and we're going to go back to sign diagrams. So for the second derivative test, you're taking your second derivative, you're setting it equal to 0, or when the function is undefined, and we're actually going to do an example of that today. Take the second derivative, you set equal to 0, find the critical points, make a sign chart. And then for the second derivative sign chart or graph, it must change from positive to negative. So we're not looking at increase, decrease, we're looking at positive, negative. So here we go, given original function f, I want to find the x values where you have a point of inflection. Okay, so that's telling me second derivative. So first we got to get down to the second derivative. First derivative is going to be 9x squared minus 2x. Second derivative of x is going to be 18x minus 2. Okay, so we have our second derivative. We need to go ahead and set that derivative equal to 0 and solve. So we're going to have 18x equals 2, x equals 1/9. And then we go ahead and make a sign chart. Okay, so I got a key, or a critical point, my bad, at 1/9. To determine if it's an inflection, we need to find the signs on each of it. So let's go to the left. I'm going to plug in 0 to my second derivative. If I plug in 0, I get an output that's negative. If I plug in a value greater than 1/9, so let's say 1, I'm going to get an output that is positive. So since we have a sign change here, we know that 1/9 is an inflection point. So I'm going to say F has an inflection point at x equals 1/9 because F double prime changes sign. You could say it goes from negative to positive, or however you want to word it. Key here is that we do have a sign change, so we do have an inflection point. So example 6, we look at a bunch of different ones. On these, they all give me the original function. We want to go ahead and find second derivatives. So for this one, my first derivative would be negative sine x. Second derivative, negative cosine x. We go ahead, set that equal to 0. And we solve it. So you're going to get x. Let's think back to the unit circle. Okay, so I'm going to draw a rough unit circle over here. You got 0, pi halves, pi, 3 pi over 2. I got 2 pi as well. All right, so on the when does cosine equal 0, it's going to be when we're on the y-axis. So it's going to be at x equals pi halves and 3 pi halves. Okay, so those are my critical points. We go ahead and make a sign chart. And still thinking back to the unit circle, we can go ahead and do a quick sign chart here. So if I want less than pi halves, I want, let's say, like right in here. My cosine value is positive because it's the x, so we have a positive. If I want between pi halves and 3 halves, I'm over in these quadrants over here where cosine is negative. And then greater than 3 pi halves, I'm back to the right. So we have an output of positive again. So we want points of inflection. We're going to have points of inflection at x equals pi halves and 3 pi halves because F double prime changes sign. Okay, for B, we go ahead and find derivatives again. So my first derivative is 1/3 x to the negative 2/3. Second derivative is going to be negative 2/9 x to the negative 5/3. If I go ahead and rewrite that, you got negative 2 over 9 x to the 5/3. Okay, for this one, if I set it equal to 0, we can't solve it at all, but we do have an undefined value. And this is going to be undefined when x equals 0, okay, because we can't have the denominator equal 0. So I can't, there's no way I can get this second derivative equal 0, but we are undefined when x equals 0, so there's my sign chart with the 0 in there. Let's go ahead and plug in positive, negative values. If I go ahead and plug in a positive value for this, we're going to go ahead and test it out. You got negative 2 over, let's go ahead and plug in 1. When I go ahead and plug in negative 2 over 1, I'm going to get negative output. I plug in a negative value, we're going to get negative divided by negative, so it gives me a positive. Therefore, we're going to have an inflection point at x equals 0. So inflection point at x equals 0 because f double prime changes sign. All right, last example for the day. They give you the original function. We can go ahead and find second derivative. So first one is 4x cubed. Second one is going to be 12x squared. We go ahead and set that equal to 0. We get a critical point at x equals 0. Sign charted up. If I plug in a positive 1, we get a positive output. If I plug in a negative 1 squared is positive, so I still get a positive output. So with this, we're going to say f has no inflection points. Because f double prime never changes signs. And in fact, we can do one better, and we can say that since the second derivative is always positive, f is always concave up. All right, so that is the first part of 4.3, part 3.